Hello and welcome back. Okay, so the code loaded on here at the moment is still my Fibonacci demo. I wasn't planning to do another coding video in the series at this point, but I had mentioned to a couple of people that I was working on multiply and I had some direct requests to do one on that. So, who am I to argue? And I was working on the function anyway, so I've assembled this into a video. So let's have a look at how we can multiply binary numbers. To start, we need to quickly go over how binary works again. So I've got here 16 columns with the binary place values, which are the powers of 2 from 1 up to 32,768. And so we can construct a binary number up to 65,535. Is a simple example, 173, 10101101. What the binary encoding is doing is wherever we see a 1, it means we're including the value for that column. This is the same as in decimal where the columns are 10, 100, 1000. We essentially can calculate the value by multiplying by the column. But since we've only got a 1 or a 0, we can basically think in terms of adding together the value of all the columns where the bit is set. Now, an operation you'll hear me mention a lot is shifting. So if we shift this number left, what we've done here is we've transposed each bit one place to the left. We've brought a 0 in here, but most of the time when we're doing this in a processor, we have the option of using the carry flag. Indeed, in my processor, the registers are 8 bits and not 16 bits. So we'd be doing 2 shifts and using the carry flag to have moved this bit from the lower byte into the upper byte. But by shifting this left, we've doubled it to 346. And we can keep going with that. So double it again to 692, double it again to 1382. So we can do a multiplication by any power of 2 just by shifting the bits by the correct number of places. And this is going to be quite useful to us when we try and put together a multiply. So these values I've calculated here are 1 times the starting value, 2, 4 and 8. Notice how these are the powers of 2. In the same way these are across the top. Let's think about how we're going to multiply a number by, say, 10. Now we could do this the absolutely naive way. We could construct a loop for 10 iterations and add x to itself that many times. In fact, for small values this may not be particularly bad. But there are faster ways of doing it. We can think about decomposing the multiplication into simpler multiplications. We don't know how to do a multiply by 10, but we do know how to do the multiplies by the power of 2. So we can look at that and say x multiplied by 8 added to x multiplied by 2 is equal to x multiplied by 10. And this is great. So what we need is an algorithm that lets us produce this sequence of multiplies and adds to multiply by any number. So let's have a look at the 10 in binary. Now what's curious here is the bits that are set in 10 are the 8 and the 2. So if we just focus on the shifted multiplications of our original number that corresponds with the bits in the number we want to multiply it by, so we're going to call this left-hand side and right-hand side, then this actually gives us a guide of which values we want to add together. So the third bit and the second bit are set, so we want the third and the second shifted version of our starting value, and if we add those together we will get the final end result, 1730. So we can see a route to an algorithm here. Okay, so now we need to think about how we can move towards program code. And the first step is to think about the registers we need. So we've got the left and the right hand inputs. Now these are going to be 8 bits in size for this multiply. I'm interested in multiplying 2 8-bit values to get a 16-bit result. And so a single 8-bit register will do for each of those. The result needs a pair of registers for the output so we can store a full 16 bits. So that's 4 registers. And now we need to think about the algorithm. Okay, now I've implemented a multiply many times before, so I'll explain the way that first occurred to me. Now we want to take one of these values and start shifting it up, and that's going to take it outside of a single 8-bit register. So we're going to need another one. So the first step of the algorithm is we're going to shift the left-hand side register right, and this will place the first bit into the carry flag. And then what we want to do is perform a conditional add of the right-hand side value as it currently exists into the result. So if that bit is set in LHS, we add RHS to the result. And then we're going to shift the RHS value to the left one, and this will be 2 8-bit shifts for us via the carry flag. And this will work. We repeat this 8 times, and then for each bit in left-hand side that is set, we'll add the corresponding shifted version of RHS into the result, and eventually we'll finish with the multiplied value. And that's brilliant. But on this processor, that does give us a small problem. This would be 5 8-bit quantities, and I've only got 4 GPRs. So I've kind of sketched out on a piece of paper the operations I'd need to do that, and you'd end up having to swap data either in and out of memory doing push and pops, or there was a route to doing it swapping in and out of TL and TH. But either way, the number of instructions for that core loop gets quite high when you do that. This is why if you look at modern RISC style processors, you find they have large numbers of registers, 16 or 32, occasionally more, because the moment you can't fit your core algorithm in registers, it slows down by a chunk. So I did look at this algorithm, and necessity breeds innovation. So I played around with this and realized there was a different way I could do it. Now, instead of shifting LHS right, I shift it left. And so we're doing the same sequence of operations, but in a different order. And instead of using 2 registers for RHS, I'm going to drop that back down to just the 1. And so what I'm going to do is test the top bit of LHS. And so instead of progressing from the bottom bit up, I'm going from the top bit down as we loop through these operations. And so I only need to do a conditional add from RHS into the low portion of the result. Now I will need to take account of an overflow here, but I've got an instruction for doing that. But then in each stage of the loop, I shift the result left by 1. And this is the benefit of going from the high bit down. So we save a register with this algorithm because that high bit that we did here, by the time we finish it, we've shifted it left 8 times and put it in the top byte. And that's pretty good. It does take away the opportunity of doing an early out if LHS hits 0, but that tends to be a little bit more complicated anyway. Okay, let's take a look at putting this into code. So let's assign what our registers are going to be. So inputs will be A times B, output will be C and D, so C will contain the low part and D will contain the high part. Made a bit of a standard of putting 16-bit values in either AB or CD. Firstly, we need to shift left either A or B. Let's make it B. Then we're going to use the same trick as we did in the divide, and we'll create a predicated add instruction. So that's add on logical carry. So then we'll need to do an inc with carry D just in case that add overflowed. We need to pay attention to how the flags are preserved in the case where the add doesn't happen. And then we need to shift left C, shift left D. Okay, technically that should be at the start. Okay, now that sequence of operations looks about right. I'm a little bit worried about the carry flags. We don't want to be shifting garbage into the bottom of C here. Doesn't matter if we're shifting anything into the bottom of B. Yeah, I don't think this is going to work. Let's do that with an add b comma b, and then the bit of interest will be in arithmetic carry. So we're going to need to create this add-on arithmetic carry instruction. And this won't work. Now the add b comma b will insert, the add b comma b will set the carry flag in the second stage of the ALU. And if we implement this the same way as we did the sub AC in the divide, then that needs it to be set in the first stage of the pipeline. So let's put a NOP in there for now. That will make this work. That's a little unsatisfactory. I may come back to that later. But even so, that's our central loop is 6 cycles long. We need to replicate that 8 times to complete the multiply. Now we've got that replicated out 8 times. Let's look at what we need to do differently. There's nothing in C or D for the shift to happen, but we do need to clear them out. Okay, that can go there. Can't see an easy way of getting rid of these NOPs right now. Let's give this code a test anyway. Let's do our 173 by 10. Okay, I had to add the implementation for add AC to the control ROM builder, but this is almost exactly the same as the predicated subtract I did for divide, so there's no reason to sit you through me doing this. Okay, so the first instruction is that moving a constant into A. So that's our 173. And we're loading 10 into B. The same bit pattern we were dealing with before. So here's that XOR C comma C coming in. So that's not going to do anything because C and D are both 0. Here's the add B comma B. So that will move this into the carry flag. Well, 0 into the carry flag, so it's not on. Okay, that is XOR D comma D, which I moved down into a NOP space, and that's actually going to break it. It won't break this because the carry flag isn't set, but that exclusive OR would reset the arithmetic carry. I need to change that into a move. C's already 0, so I can copy C into D and that'll be okay, but let's not forget that. Here's our new add, only if arithmetic carry is set, which it's not. And there's the increment on carry, which will also not do anything to D. And then we've wrapped to the shifts for the first of the next iteration in the algorithm. So nothing much is going to happen until this bit gets shifted all the way up to the top. So now we've got an arithmetic carry. Here's our predicated add, which should add A to C in this case. Yes. There's a no carry flag set, so this inc on carry is not going to do anything. And now we're doing the shift left of C and then D. So that's a 16-bit shift between those two registers. That's worked in both cases. Right, so we've got 110, 11, 000, 010. So that's 1730 as we wanted. Outstanding, that has worked. Okay, so I want to take this code and turn it into a function. Okay, that's a little bug fix we realised we needed. We're going to corrupt B. So I want to save and restore that to play nicely with any calling code. Each of these are 6 cycles. We've got 7 of those. This is 5 cycles. Push at the start is 2. And we've got 2 and 2. I could possibly actually move that increment down into the branch delay slot behind the return, but I'm not going to do that right now. At the moment, that's 4 cycles at the end. Okay, so I make that 53 cycles. Let's quickly look that up in the 8086. Right, so the original 8086 is 70 to 77 cycles. Excellent. Even having to code it out and include these NOPs in to deal with the flag not being quite ready, we are still outperforming the original 8086 in the same operation. I like it. I'm happy with that. Right, I think what I'm going to do is write a slightly more interesting bit of code to put this through its paces, and I'll be back in a moment. Okay, now I have written a very basic number squaring program. So I've just got a counter that goes through and squares the result using the multiply function and outputs onto the LCD. So I've checked a bunch of these and I'm pretty confident this is working correctly. So that effectively demonstrates the multiply. It's taking its time though because it's got 255 iterations through the loop. Let's try that. A little bit faster. But that's my clock going as fast as it will. At some point I'm going to need to look at this clock module again, because with the bigger programs that we're starting to write, it's could do with going a bit faster, and I'm pretty sure the circuit will support a much higher rate than we're currently generating. I should throw the scope on at some point and find out how fast it actually is. Well, I hope you found this one interesting. The multiplier was a stepping stone along the road to the more interesting demo that I've been working on, and so I didn't really waste too much time with it apart from the video editing. So I hope you found this interesting. I'll see you again soon. Goodbye.